Your program just froze. No crash, no error message. It's just sitting there doing nothing. You check the logs. Nothing, you check the CPU. Idle, the program is alive, but it will never make progress again. This isn't a bug in your logic. This is a deadlock. Here's what happened. Process 1 grabbed resource A and now needs resource B to continue. But process 2 already holds resource B, and it needs resource A. Each process is waiting for the other to release what it holds. But neither can release, because neither can finish. They're trapped forever. This is one of the most subtle and dangerous problems in computer science. Deadlocks don't crash your program. They silently freeze it, and they've plagued operating systems, databases, and distributed systems for decades. Today, we're going to understand exactly how deadlocks work, why they happen, and most importantly, how to prevent them. So what exactly is a deadlock? Formally, a deadlock is a state where two or more processes are permanently blocked, each waiting for a resource that is held by another process in the same set. No process can proceed because each one is waiting for something that will never be released. Think of a four-way traffic intersection with no traffic lights. 4 cars arrive at the same time, each blocking the car to its right. No car can move forward because each one is waiting for the car ahead to clear. Complete gridlock. Now, deadlocks are often confused with two similar problems. Starvation is when a process keeps getting skipped because higher priority processes keep cutting in line. The process could eventually run, it just never gets the chance. A livelock is when processes keep changing state in response to each other, but no actual progress is made. Like two people in a hallway stepping side to side, trying to let each other pass. A deadlock is permanent, nothing changes, nothing progresses ever. To build intuition for deadlocks, let's look at one of the most famous problems in computer science: the dining philosophers problem. 5 philosophers sit around a circular table. Between each pair of philosophers, there is exactly 1 fork. To eat, a philosopher needs both the fork on their left and the fork on their right. Each philosopher thinks for a while, then gets hungry. When hungry, they reach for the left fork first, then the right fork. If they get both, they eat, put the forks down, and go back to thinking. Sounds simple enough, but here's the problem. Imagine all 5 philosophers get hungry at the same time. Each one picks up their left fork. Now every fork on the table is held by someone. When each philosopher reaches for their right fork, it's already taken by their neighbor. Nobody can eat. Nobody will put their fork down because they're all waiting for a second fork that will never become available. This is a deadlock, a perfect circular chain of waiting. In 1971, Edward Coffman and his colleagues identified the 4 conditions that must all hold simultaneously for a deadlock to occur. These are called the Coffman conditions. The first condition is mutual exclusion. At least one resource must be non-shareable. Only one process can use it at a time. The second condition is hold and wait. A process must be holding at least one resource while simultaneously waiting to acquire additional resources held by other processes. The third condition is no preemption. Resources cannot be forcibly taken away from a process. A process must voluntarily release its resources. And the fourth condition is circular wait. There must be a circular chain of 2 or more processes, where each process is waiting for a resource held by the next process in the chain. Here's the critical insight. All 4 conditions must hold at the same time for a deadlock to exist. If you can break even one of these conditions, a deadlock becomes impossible. This is the foundation of every deadlock prevention strategy. Now let's look at how we can visualize deadlocks using resource allocation graphs. In this graph, processes are represented as circles and resources are represented as squares. We draw 2 types of edges. A request edge is a dashed arrow from a process to a resource, meaning the process is waiting for that resource. An assignment edge is a solid arrow from a resource to a process, meaning the resource is currently allocated to that process. Let's build one step by step. Process 1 holds resource A, that's an assignment edge from A to P1. Now process 1 requests resource B, that's a request edge from P1 to B. Meanwhile, process 2 holds resource B and requests resource A. Look at the graph now. Follow the arrows. P1 points to B, B points to P2, P2 points to A points to P1. We've formed a cycle. And a cycle in a resource allocation graph means we have a deadlock. If there is no cycle, there is no deadlock. The graph makes the problem visible. So how does an operating system actually detect deadlocks? The answer is a wait for graph. This is a simplified version of the resource allocation graph we just saw. Instead of showing resources explicitly, we only show processes and draw an edge from process A to process B if A is waiting for a resource held by B. The operating system periodically builds this graph and runs a cycle detection algorithm. Essentially, it performs a depth-first search. Start at a process, follow the wait edges, and if you ever reach a process you've already visited, you've found a cycle. A cycle means deadlock. Once a deadlock is detected, the OS has to break it. The most common approach is to terminate one of the processes in the cycle. Databases typically roll back the youngest or cheapest transaction. Some systems can preempt resources, forcing a process to release what it holds. The trade-off is clear. Detection lets deadlocks happen but catches them quickly. The question is how often to check. Too frequent wastes CPU. Too infrequent lets deadlocks persist. Instead of detecting deadlocks after they happen, we can prevent them by ensuring at least one of the 4 Coffman conditions can never hold. To break mutual exclusion, make resources shareable when possible. Read-only locks, for example, can be held by multiple processes at once, but some resources, like printers, are inherently non-shareable. To break hold and wait, require each process to request all resources it needs before it starts executing. If any resource is unavailable, the process waits without holding anything. The downside is reduced resource utilization. To break no preemption, allow the operating system to forcibly take resources from a process. If a process is waiting and holds resources, those resources can be reclaimed and given to others. But the most practical and widely used strategy is breaking circular wait. Assign a global ordering to all resources. Every process must request resources in increasing order. If you need resource 3 and resource 7, you must acquire 3 first, then 7. Never the other way around. This simple rule makes circular dependencies impossible. It's the strategy most real-world systems rely on. Prevention is conservative. It restricts how resources can be requested. Avoidance is smarter. It allows flexible requests but checks each one before granting it. The most famous avoidance algorithm is the banker's algorithm, designed by Dijkstra. Think of the operating system as a banker with a fixed pool of resources. Each process declares its maximum resource need upfront. The OS tracks 3 things: how many resources are currently available, how many each process currently holds, and how many more each process might still need. The need of a process equals its maximum minus its current allocation. When a process requests resources, the OS pretends to grant the request and checks. Is the resulting state safe? A safe state means there exists at least one ordering of processes where everyone can finish. If the state is safe, the request is granted. If it would lead to an unsafe state, the request is deferred until later. An unsafe state doesn't guarantee a deadlock, but it means one is possible. The banker's algorithm ensures we never enter that risky territory. Deadlocks aren't just a textbook problem. They happen in production systems every day. In databases, deadlocks occur when 2 transactions update the same rows in opposite orders. Transaction A locks row 1, then tries to lock row 2. Transaction B locks row 2, then tries to lock row 1. Classic circular wait. Database engines like PostgreSQL and MySQL detect these using wait for graphs and automatically roll back one transaction. In multithreaded code, the most common cause is acquiring mutexes in inconsistent order. Thread 1 locks mutex A, then mutex B thread 2 locks mutex B, then Mutex A the fix is simple. Always acquire locks in the same global order, regardless of which thread you're in. In distributed systems, deadlocks are harder to detect because there's no single process with a global view. Service A sends a request to Service B and waits. Service B sends a request to Service A and waits. Both are blocked. The standard solution is timeouts. If a response doesn't come within a deadline, assume failure and retry. The theory we've covered maps directly to every one of these scenarios. Let's bring it all together. Deadlocks are one of the most subtle bugs in concurrent systems. They don't crash your program, throw an exception, or fill your logs with errors. They just silently freeze everything. But now you understand the framework. 4 conditions must all hold simultaneously: mutual exclusion, hold and wait, no preemption, and circular wait. Break anyone, and deadlocks become impossible. You know how to visualize them with resource allocation graphs. You know how operating systems detect them with wait-for graphs and cycle detection. You know the banker's algorithm for dynamic avoidance. And most importantly, you know the simplest and most effective prevention strategy in practice. Always acquire resources in a consistent global order. Whether you're writing database transactions, multi-threaded code, or distributed services, this single rule will save you from the silent freeze. That's how deadlocks actually work.